We will now talk about the architecture of 8085. The architecture of 8085 actually starts from the program counter. The program counter contains the address to the next instruction. A little bit of background. 8085 is basically based on the concept of stored program, which means the program we want to execute is initially stored in the memory, and that particular program is fetched time and again and executed for a certain operation. Now, talking about the memory contains a lot of cells, and each cell address is represented using 16-bit. So it starts from 0000 to FFFFH, and the content of the memory are of 8-bit. Okay, so the program counter, as I told you, contains these particular addresses of a particular instruction that is supposed to be fetched for execution. Now, the 16-bit address is divided into two parts, basically the most significant 8 bits and least significant 8 bits, and then multiplex data, and then address bus as well as the multiplex data and address bus are used to point to a certain memory location from where the instruction is supposed to be fetched. Once the memory location is identified, the 8-bit instruction is then taken out to the data address buffer here. You can see this is bidirectional while the address buffer is only unidirectional, and that particular instruction is now taken via the data bus to the instruction register. Once the data reaches the instruction register, it is then passed to the instruction decoder, where the actual instructions are decoded, and then based on the understanding of the instruction or what it is supposed to do, the timing and control circuit sends necessary control signals to required components of 8085. Now, whenever we talk about fetching data from the memory or doing some memory operations or doing some arithmetic and logical operations, let's do arithmetic and logical operations from the registers first, and then we can go to the memory. We see that there are some programmable registers here, BC, DE and HL. Each of these are of 8 bits, but we can also use them in pair and then use them as 16-bit registers, but we have to use them in pair. There's also a register called WZ, but this is not accessible to us. So the register BC, DE and HL are general purpose registers which we can use during programming. Now, any value in these general purpose registers, if we are supposed to, let's say, add two values present in register B and register D, then those two values are taken via the data bus to the accumulator. One value is taken to the accumulator, and then the other value is taken to the temporary register here. Then these two values goes to the arithmetic and logical unit, and then basically the data manipulation operation happens here. Now, the instant the data manipulation operation execution is done, the flags are updated. We have 5 flags basically of 8-bit. So these 5 flags will be updated, and then they will also be accessible again to be used in further operations here. Now we have interrupt control, which are basically used to generate interrupt to the microprocessor from the external peripherals connected to it. So basically, microprocessor might be doing some task at an instant. We might have connected a keyboard somewhere in one of these pins here, and then maybe the keyboard, and maybe we're supposed to ask the microprocessor to read the data from the keyboard at a particular instant. So in that case, microprocessor is supposed to halt its current operation and then basically respond to the interrupt generated by the keyboard or the externally connected peripheral to it here. Also, we have a serial improper control. This is basically provided for interfacing such peripherals that transfer or receive serial data in this case. So to summarize this, we have a program counter that contains the next instruction. We also have address data buffer and then the address buffer, which basically breaks down the 16-bit address into 8-bit addresses, and then we go to the memory and then fetch some instruction from the memory to the data address buffer, and via the data bus bring it to the instruction register. And from there the instruction goes to instruction decoder. The instruction is decoded, understood, and then the timing and control circuit takes care of the rest. There is also an accumulator and a temporary register in which the values are loaded either from the memory down here, or from the general purpose registers that we have. So the data source can be from anywhere, either from the memory or the general purpose registers. The data manipulation operation happens in ALU here, and then we also have a flag flip flop. Basically 5 flags are present which updates the status of the result in ALU. Again, they can be used. There is an 8-bit internal data bus in the entire system here. The serial input output control is responsible for interfacing peripherals or input output devices that transmit serial data, and the interrupt control contains some pins which are used to generate external interrupt or hardware interrupt into the microprocessor. Also, we have this stack pointer here. So the main task of this stack pointer is that the program execution might not always be sequential. For example, let's say that we start from this particular memory cell, so up to a certain line, let's say up to this line, the program execution is sequential. Then from this line we might introduce something like a call function, and that particular call function code is present in this particular location. So in that case, the program does not go down here. Now it jumps to this particular location, and after execution of this, the program has to go back to its last location, so to continue the execution. So during such jumping scenario, or breaking the procedural oriented scenario, the microprocessor has to know about where it broke off from and then where it needs to go back. In that case, such addresses are stored in stack pointer here. The increment decremental latch actually increases or decreases the program counter as per our need. So this is it for the architecture of 8085.